Here are some formulas you may have learned about sequences in Algebra 2 or Pre-Calculus. Go ahead and start by simplifying n plus 2 quantity factorial over n factorial. If you have something to a factorial and you need to expand it, we're going to follow this expansion definition. If you're expanding n factorial, your first term is n. So if you're expanding n plus 2 quantity factorial, then your first term is n plus 2. And each time we see n, we're going to replace it with an n plus 2. Let's go ahead and simplify. At any time in a factorial expansion, instead of putting the dot dot dot, I can put my factorial symbol on the last term, and it will be notifying us that this does continue to expand. So what if I take away this term? Can I just put a factorial on this term and it mean the same thing? Yes, because this n factorial could continue expanding, and so we're not removing any of the other terms, we're just abbreviating that notation to be just a factorial symbol. N factorial over n factorial is just a special form of the number 1, which leaves us with n plus 2 times n plus 1. Go ahead and write out the first 5 terms of the sequence a subscript n, also known as a sub n, if a sub n is equal to n over n plus 1. A subscript 1, or a sub 1, will be our first term. We'll plug in 1 for all the n's. A sub 2, you'll plug in 2 for n, and continue finding the rest of the terms. Number 3, write out the first 5 terms of this recursively defined sequence, where the first term is 5 and the next term is equal to 3 times the term before plus 4. A sub 2 is equal to a sub 1 plus 1, meaning k will equal 1. 3 times a sub k, a sub 1 in this case, plus 4. A sub 1 is 5, so 3 times 5 plus 4, which is equal to 19. Our next term will be a sub 3, which would be a sub 2 plus 1, making k 2. We know a sub 2 is 19, which simplifies to 61, and continue. To write a recursive definition for this sequence, we want to find what kind of a pattern is going on between each of the terms to see what... Nah, we don't need to see anything after that. From 2 to 6, I can multiply by -3 or subtract 8. And from -6 to 18, multiply by -3. Okay, it looks like this is a geometric sequence, because it has a common ratio, a number that you're multiplying each term by to get the next term. So for a recursive sequence, we're going to state what the first term is, because you always need a starting point, and then the term after that, we'll call that a sub, and then any term after that, we'll call that a sub n plus 1. We'll take the term before and multiply it by -3. Keep in mind that the entire formula also involves the a sub 1 equals 2. If you do not give a starting point for a recursive formula, then you haven't given the entire formula because you don't know your starting point. Now we're going to write an expression for the nth term of the sequence from number 4. Because this is geometric, we'll use the formula for an explicit geometric sequence. A sub 1 is your first term, r is your common ratio. And there's your answer. If a sub n is a sequence, and the limit as n approaches infinity of a sub n equals L, then L is the limit of the sequence and it converges to L. Find the limit of the sequence b sub n. He's waiting for me to finish this so we can work on homework. But you should start it without me.
Nah, I'm doing other work. I forgot to do one of the assignments, and he sent me an email. I was like, why did you do the assignment? And then he just excused it. Whatever.
Yeah, college is very different. Just like, why do you do it? Oh, just give me credit. It's fine.
Yeah, he said as a one-time courtesy. I kind of want to not do it again. Just
As we take the limit of the sequence as n approaches infinity, we get a number, negative 1/2. Therefore, the sequence b sub n converges to negative 1/2. If the limit of a sub n as n approaches infinity does not exist, then the sequence a sub n does not have a limit and a sub n diverges. Determine if these sequences converge or diverge and find the limit if possible. The limit of our first term is just 3, the constant. But the limit of negative 1 to the n as n approaches infinity, if you have negative 1 to an odd power, then your result is negative 1. If you have negative 1 to an even power, then your result is positive 1. So this piece just continues to alternate between positive 1 and negative 1, which means the limit does not exist because negative 1 to the n oscillates. 3 plus does not exist means that it does not exist. If the limit does not exist, then this sequence diverges. Let's find the limit as n approaches infinity of b sub n. Look, we got a number, L. Therefore, the limit of this sequence is 2, and this sequence converges to 2. As a reminder, the curly braces signify that b sub n is a sequence.
a sequence is monotonic if it is non-increasing or non-decreasing, meaning each term is greater than or equal to the one before, or each term is less than or equal to the one before. A sequence is bounded if every term is greater than or equal to some number n, the lower bound, and also every term is less than or equal to some number m, the upper bound.
A monotonic sequence converges if and only if it is also bounded. A bounded sequence can either converge or oscillate. Negative 1 to the power of n will oscillate between 1 and negative 1, and then you're adding 3, making our lower bound 3 plus a negative 1, and our upper bound 3 plus 1. As we established, a sub n is an oscillating sequence, so it cannot be monotonic. However, it is bounded between 2 and 4. As a reminder, the limit of the sequence b sub n was 2, so this sequence will converge to 2. We can check for if this is monotonic, non-increasing, non-decreasing, by checking the first few terms. B sub 1 would be 2 over 2. B sub 2 would be 4 over 3. B sub 3 would be 6 over 4. And if we continued, I believe we would have a non-decreasing sequence. Each term is greater than or equal to the term before, making the sequence b sub n monotonic. A monotonic increasing sequence that is bounded because there is a limit as n approaches infinity. You can also think of bounded similar to the horizontal asymptote of the sequence's corresponding function. Another reason we know this is bounded is because if it's monotonic and it converges, it has to also be a bounded sequence. Check the limit as n approaches infinity of a sub n to see if it converges. Yes, it converges to 0. In fact, our horizontal asymptote is y equals 0. So it is bounded by 0. Below. 1 over n, as n approaches infinity, we're approaching 0. This is monotonic decreasing. And remember, if it's monotonic and bounded, then it converges, which would make number 10 a converging sequence and number 9 a divergent sequence. And our last one, number 12, First, take the limit as n approaches infinity of the sequence. Our limit is infinity. This is definitely not a bounded sequence. But if we're headed toward infinity, it's probably a monotonic, non-decreasing sequence. And you can always plug in 1, 2, 3, 4 to make sure that these terms are increasing. As we approach infinity, each of our terms is greater than or equal to the term before, meaning this sequence, even though it is unbounded, is still monotonic, non-decreasing. And because it is unbounded, it is a divergent sequence.